going to explain the concept of Newton's method to approximate the zeros of the function. And in this case, we are going to use a quadratic function. And as you know, for quadratic functions, we already have formulas. For example, we can find the points where our function crosses the x-axis. It simply means at these points the value of y is 0, the value of the function is 0. So we write in general case, we write the formula for quadratic equation is ax squared plus bx plus c. Then we rewind, and you can see for quadratic formula there will be two places where the y, the function crosses the x-axis, and it will be b minus plus square b squared minus 4 ac divided by 2a. Plus minus means like the plus will the result of the plus will be one of the root, and the minus will be the another root. But we have another method, and I want to talk about the Newton's method for finding this. And actually, in this formula, we exactly find those points. But in the Newton's case, we can't find the exact points. We'll try to approximate those points with some precision. And how do we do it? I want to show it geometrically. And this method is important because it's a very essential concept in nonlinear optimization. And then after understanding how we use Newton's method for approximating the zeros of the function, we can generalize it into a method where we can use it for optimization problems. So that's why I wanted to start with Newton's methods for finding the zeros of the function. And how it works. To understand it, we have to go back to the idea of the derivative. When we calculate the derivative of a function at point x, we write it as f x0, let's say x0 is fx1, we write fx0, fx1 minus fx0 divided by x1 minus x0. And we find we want to find where this function approaches as x1 gets closer, x0 gets closer to x1. Okay, we find it, we know this. So what does it mean geometrically is that, for example, we have point x0, let's say it's here. We have a point x0, and we have, and this is fx0. To find the derivative of this function at this point simply means that we find the slope. And we are lucky because as we zoom in, it exactly looks like a line. And how do we do it? We have the slope, and I won't go into the details what is the geometrical meaning of the derivative, because I assume that we already know that. So this is the slope of that function at a point x0. So f x0 is the slope of that function at that point. The derivative of x0 is the slope of that function at x0. And let's try to do something. We have x0, we have the point, we have the slope, and let's try to draw a line. That whose slope is the same as this one. So what it means is that we draw a line. I will draw a line. Okay, let's make it some. Okay. Okay, it seems accurate. Okay. So we drew this line. It's simply the tangent of this point, which is the slope. So we draw this line, and what we know about this line is that we know the slope of this line. We know the point that it passes through. It's x0 and fx0. It should pass through that point, and we know the angle that this line goes through that point, and we also know that at some point this function, this line passes a point whose y-coordinate is 0 at this. Oh, sorry. Okay, 0 and this is let's denote it as x1 and 0, x0. So we have a line. We have a line that we know that passes through these the points. It passes through from x0, fx0, and x1, 0. And we also know that the slope of this line is fx0. The derivative of f at x0. So I want to remind you that we also have the formula for the slope of this function that we can derive from when we have the 2 points that we know this line passes through. So it will be fx0 minus 0 divided by, because these are the y-coordinates of the line, that's y-coordinates of the points that this line passes through, and x0 minus x1 is equal to f derivative x0. Interesting. Because we know this is the slope, and we drew a line with the same slope, and also we have the formula that calculates that slope, then it's obvious that these are equal. And from this formula, let's try to find out x1. Let's try to find out x1. How do we find it? Let's just do some operations. x0, x1 is f x0, then we have f derivative x0, x0 minus f derivative x0, x1 is fx0, and then we have f, we just keep it, we write f x0, x0 minus fx0 divided by f x0 is x1, right? x1. And what we can do, we can divide these by f derivative at the x0, then it will be x0 minus f x0 x1, right? So we have the formula. x0 minus the derivative of that function at x0, oh sorry, no, and not the derivative, just the value of that function at x0 divided by the derivative of that function at x0. So with this formula we can find this. We can find this. So we know what is x. Once we know x, we can repeat the same process one more time. Then how it will look? It will look like this. This is our new point. And then we will do the same process and draw that line one more time. No. Okay, one more time. Okay, let's do it. Okay, now we have this. Now we have this. Then we'll try to find x2. Oh no. Okay. And then we try to find the x2. Then x2 will be x1 minus fx1 divided by f x1, right? And if we keep doing that, as you see, for example, let's say we are here for the second one, the line will be something like this. It will, I don't know if it will be visible, then it will be like this, like this. As you can see, as we keep doing it, the distance between, for example, this one x0, x1, x2, the distance gets closer and closer to each other, and we're getting closer at the same time. We're also getting closer to the point where our function has a value of 0. It means that the y of that function is 0. So you can ask, when do we stop doing it? When do we stop doing it? For example, we can get x, sorry. Oh, no. Come on. I'm sorry, guys. Anyway. Okay. So we'll keep doing it as xn. Maybe we should increase. Is x n minus 1 minus f x n minus 1. Or we can just write like this: x n plus 1 xn and xn divided by f xn. And we keep doing it until, and we know as we get closer to the point where the function, as we get closer to the root of that function, the distance between our xn and xn plus and n plus 1 and xn also decreases. So we can use that fact, we can exploit that fact that where the distance between xn plus 1 and xn gets decreases, then we can set a threshold and say when the difference between xn plus and xn is this small number, then stop. If is some small number, then stop, because it can go infinitely. It's an approximation. We just need a point where this difference is really small. Then we say, okay, we have really good approximation of the zeros of that function. Yeah, that was a bit long video, and I hope you liked it.